Index. Introduction 1. The 2C Imperative 2. Deforestation 3. Energy Efficiency 8. 4. Wind Energy 5. Hydroelectricity 6. Bioenergy 7. Natural Gas 8. Carbon Capture and Storage CCS 9. Regional Case Study. The 2C Imperative. The average global temperature has already risen by 0.74 C in 2005 compared to 100 years ago, and 11 of the last 12 years, 1995 to 2006, rank among the 12 warmest years in the instrumental record of global surface temperature. Scientists attribute most of this temperature rise to human activities which release carbon dioxide CO2 and other greenhouse gases GHG into the atmosphere. According to recent research, an average global warming of 2°C or above compared to the pre-industrial revolution level would result in dangerous and irreversible impacts, including the following projections. Water shortages globally. More than 3 billion more people would be at risk as a result of water shortages. The predicted loss of ongoing glacier meltwater in India alone would cause water shortages for 500 million people and for 37% of India's irrigated land. Food insecurity. More frequent droughts in Africa and elsewhere would lead to lower crop yields, and there would be a general decrease in cereal crop yields extending beyond the tropics to mid-latitude and temperate regions, mainly due to increased evapotranspiration. Health impacts. 300 million people would be at greater risk of malaria and other vector and waterborne diseases, and the health costs of climate change are projected to double by 2022, partly as a result of heat stress, but primarily because of increased rates of diarrhea and malnutrition in low-income countries. Socioeconomic impacts. Initial estimates of socioeconomic losses with moderate temperature increases include gross domestic product GDP losses of a few to several GDP percentage points, with net global damage of up to 20% for unmitigated climate change compared to much lower abatement costs in the case of early mitigation action. Effects on ecosystems. 35% of terrestrial species would be at or near extinction by the year 20505, including the loss of unique ecosystems/species, e.g., the Cape region, South Africa. Solution. Research indicates that at 550 ppm parts per million CO2 equivalent CO2e, the likelihood of exceeding 2°C above pre-industrial levels is very high, 63 to 99%, with a mean of 82%. Stabilization at 475 ppm would bring with it a 38 to 90% mean, 64% probability of exceeding a 2°C target. With a stabilization at 400 ppm CO2e, the probability of exceeding 2°C unlikely, with a range of 8 to 57% mean, 28%. Greenhouse concentrations already exceed 400 ppm CO2e. However, there will be some ray absorption by the biosphere, land and oceans, and analysis by Munchausen indicates that in the short term radioactive forcing by greenhouse gases is being offset by aerosol emissions from industry and biomass burning, amongst other things. Deforestation. Deforestation is responsible not only for significant ecosystem and species loss, but importantly also for 20% of global greenhouse gas emissions. 10 countries account for 87% of global deforestation, with Brazil and Indonesia alone accounting for 54% of these emissions. Tropical forests, where deforestation is most prevalent, hold over 210 GTC and almost 500 GTC in their soils, which is often released in land use change. Rates of deforestation have remained constant over the last 2 decades, and without significant concerted action these could result in emissions of 10 GT of carbon dioxide per year for 50 to 100 years. Forests also absorb carbon dioxide, so increasing forest cover can increase carbon sequestration, but the positive impact of this is far outweighed by the negative impact of deforestation on atmospheric carbon dioxide, let alone wider ecosystem impacts. So, while restoring forest cover is a benefit, the primary focus should be to reduce deforestation. Challenge. The causes of deforestation are wide-ranging and vary by country. They include agricultural expansion, cattle ranching, infrastructure development, and logging. These are driven by both population pressures and increased levels of local and foreign consumption, and exacerbated by poor governance and inadequate land use planning. Governments and the wide range of market actors must be effectively influenced to reduce these threats. Currently available data are provided by national governments and are not globally consistent. Establishing accurate data, and in particular agreeing new globally consistent definitions of deforestation and degradation at a forest biome level, is essential. Bioenergy is potentially CO2 neutral. However, the expansion of palm oil and tropical crops, such as sugarcane, for biofuel production could become a significant driver of deforestation. Bioenergy developments must therefore be appropriately regulated to prevent further deforestation. Solution ways to reducing deforestation must go hand in hand with improving the welfare of cultivators at the forest frontier. Any policy that does without the other is unacceptable. There are no general solutions and strategies since these will vary with region and will change over time. All strategies require cooperation and goodwill. Effective implementation is essential, including stakeholder participation, development of management plans, monitoring, and enforcement. The strategies should be such that on one hand they should recognize the critical roles of national, state and municipal governments and on the other hand empower the civil society and the private sector to take a proactive role in reducing deforestation, often working in conjunction with government. It is plausible to have the current rate of deforestation by 2015 and achieve a zero rate this year. This would lead to cumulative emission reductions of 55 gt carbon dioxide this year and 155 gt by 2030. In contrast, to have the rate of deforestation this year and achieve a zero rate by 2030 would result in cumulative emission reductions of 27 gt carbon dioxide by 2020 and 105 gt by 2030, a significantly lower benefit. Reduce population growth and increase per capita incomes. Reduction of population growth is pivotal in reducing deforestation in the developing countries. Consequent of reduced population, increase in per capita income will occur as a consequence of increased incomes and literacy rates, which will reduce pressure on the remaining forests for new human settlement and land use change. Increase the area and standard of management of protected areas. The provision of protected areas is fundamental in any attempt to conserve biodiversity. Protected areas alone, however, are not sufficient to conserve biodiversity. They should be considered alongside and as part of a wider energy efficiency. Most societies are massively wasteful of energy. Energy efficiency measures across all sectors can play a huge, essential, painless, and non-controversial part in ensuring a sustainable energy future. Such conclusions have been reconfirmed many times. The International Energy Agency's latest scenarios estimate that, depending on the scenario applied, it could account for 31 to 53% of the total carbon dioxide emission reduction relative to baseline in 2050-10. This is consistent with the findings of the JMG model, where energy efficiency technologies and systems account for a reduction of approximately one-third of energy demand. The European Commission estimates that measures could cost-effectively deliver a 20% reduction in today's energy consumption in the European Union by this 2020, with savings of at least 60 billion. 11. Energy use in commercial and residential buildings accounts for 35% of today's global final energy consumption, 32% for industry and 26% for transport. In all sectors, major savings could be achieved by adopting best available technologies, innovative materials and/or new processes and systems, in most cases available on the market and at reduced net costs, generally higher investment cost but lower operating cost. Measures in buildings comprise mainly envelope and insulation materials, lighting and appliances, heating and cooling systems. In the long term, the biggest saving potential can be achieved by setting building codes for construction and renovation for all buildings. In the short term, major savings from a better energy and use can be attained. Countries could save some 322 mt of CO2/Y by 201012 with new policies aimed at residential uses of energy, e.g., early replacement of inefficient appliances, energy labeling and systems, or setting minimum requirements for energy-using products. Industrial includes many devices and systems already commercially available, providing the same service or commodity with lower energy input. Due to the multiplicity of industrial production and processes, different technologies and systems, e.g., higher efficiency motor systems, residual heat recovery, fuel substitution, efficient steam generation and use, are applicable to a range of different sectors and industrial groups. Assessing the potential requires a detailed analysis of each technology and its application. In the past 25 years, transport emissions have grown at approximately twice the rate of improvements. Without a significant intervention, global transport GHG emissions will keep growing steadily 50 to 100% by this year 2020 in comparison with 1995. Vehicle efficiency must be further improved, e.g., increased fuel efficiency, minimum efficiency requirement for automobile AC systems, better tire rolling resistance, but at the same time measures are needed to reduce vehicle use, which would otherwise increase with improved efficiency. Wind energy today. Wind energy, most of it onshore, has a global generating capacity of about 60 GW, about 0.5% of global power, rising potentially to about 1000 GW, 12 to 18% of global power by this year 2020. This high growth potential is due to a combination of factors, including an annual growth rate of about 25% already established for many years, a rapid decline in turbine manufacturing costs with economies of scale, the size and efficiency of new generation wind turbines, expected exploration of the high renewable power potential of offshore wind, increasing concerns regarding climate and security of energy supply, strongly favoring domestic and relatively affordable renewable power such as wind. 16 Europe has the largest share of wind power globally, both in terms of manufacturing and generation. About 75% of global wind power is produced in the EU, most of it in just 3 countries: Germany, Denmark, and Spain. These all have generous renewable energy support schemes and sophisticated grid management, servicing more than 50% of all global wind generating capacity installed. Outside Europe, developments have been slower off the mark, but high current growth rates are expected to be sustained in the United States 20% PA, India and China 30% PA. Wind power currently employs about 65,000 people in the EU, growing to almost 200,000 by 2021 under the expansion scenario. Wind power globally creates 2 to 10 times more hours of employment than nuclear, natural gas, or coal per unit of electricity generation, thus contributing favorably to sustainable jobs. If the savings in pollution costs are not considered, wind energy generation is relatively expensive, 4 to 8 cents/kWh globally in 2006, up to nearly 3 times the lowest unit cost of conventional fossil fuel power production, 3 to 6 cents/kWh for modern gas or coal without CCS20. It is, nevertheless, cheaper than many estimates for current nuclear power production. However, by 2050 costs are predicted to have decreased, placing wind on a level with conventional coal, and probably much cheaper than coal with CCS. Currently, offshore wind power at about 10 cents/kWh is still more expensive than onshore. However, a recent large-scale economic analysis has predicted that in 10 to 15 years offshore costs may be halved. Offshore wind represents the largest development potential. Recent turbine-size development of towers of 5 MW plus capacity will allow more power to be generated by fewer turbines in wind parks, including actually replacing existing low-capacity onshore wind turbines. Apart from China and India, the United States will have the most dynamic national wind energy market. In Europe, a large offshore supergrid ranging up to 3,000 kilometers from Scotland to Portuguese Atlantic waters is being planned in order to establish wind power as a real base load alternative to existing large power stations. Appropriate international grid management will reduce the effect of local intermittency, one of the current shortcomings of wind power, allowing wind to provide a reasonably steady and predictable supply of energy around the clock. Bioenergy. Biomass is the totality of plants in the terrestrial and marine biosphere which use carbon dioxide, water, and solar energy to produce organic material. It also includes animals and agents of decomposition such as bacteria and fungi whose activity releases carbon dioxide into the atmosphere. Bioenergy can be derived from biomass in the form of liquid biofuels processed usually from energy-rich crops, wastes including renewable municipal waste, solid biomass, wood, charcoal, and other biomass material, or gases derived from biomass decomposition. Globally, biomass currently provides around 46% of bioenergy. This share is estimated to be over 10% of global primary energy supply, though the volume of traditional biomass consumed in developing countries is in certain applications vary widely, from traditional biomass use such as cooking on open fires in the poorest countries to highly efficient electricity and heat production or transport fuels. About 110 to 250 produced from biomass C development/deployment would remove about 819 gt carbon per year from the atmosphere if it is used to displace fossil fuels. However, this assumes the same efficiency for all biomass and that it is all produced sustainably and replanted so as to be carbon neutral. Since much biomass is used less efficiently, the actual savings would be lower. Issues and constraints. Uncontrolled development of bioenergy crops can have dramatic impacts on humans and the environment. What, where, and how the raw materials are produced and processed will define whether bioenergy projects are environmentally and socially sustainable on all fronts. I believe that key principles and criteria which must be taken into account for sustainable bioenergy production and use include the following. Bioenergy must deliver greenhouse gas GHG and carbon life cycle benefits over conventional fuels. Energy crops to be used for bioenergy must be selected on the basis of the most efficient carbon, soil and air, and energy balance from production through to processing and use. This is not always achieved. For example, energy-intensive fertilizer input increases nitrous oxide N2O emissions, a highly potent GHG, and intensive cropping may contribute to the release of soil-bound carbon dioxide. Some conventional crops, such as sugarcane or woody biomass, can provide net benefits if sustainably produced and processed, and are already available for use as bioenergy. However, future investments and research should be oriented towards lignocellulosic or other crops that offer better options to reduce carbon dioxide emissions, as well as a reduced impact on the environment. Bioenergy developments must ensure gas and climate change targets as a source of energy. Natural gas has a carbon footprint about half that of coal. Currently, coal supplies 23% of the world's primary energy, yet contributes 37% of global GHG emissions. In the power sector, the E projects that coal consumption will almost double by 2030, with China and India accounting for 68% of this increase. Whatever the exact figure, it is clear that coal use will increase hugely if alternative sources of energy are not made commercially available. Natural gas may be part of the medium-term solution. Some modern conventional power plants can be easily modified to switch fuel sources, delivering immediate carbon dioxide savings when substituting coal for gas. Furthermore, modern combined cycle gas turbine (CCGT) installations emit only 40% of the carbon dioxide produced by a conventional coal-fired power station. So displacing coal with natural gas in the power sector can reduce short and medium-term emissions, buying time for the deployment of truly sustainable zero-emission solutions and reducing the overall atmospheric loading from GHG pollution from coal. For such an outcome to occur, it is critical that gas replaces only coal use and that its use does not slow or hinder renewable energy development in the same markets. Issues and constraints: renewable energy overlap in some cases. Market conditions which price carbon will tend to favor gas, which is a competitive energy supply in most markets, over renewables, which would need a higher carbon price to compete directly with gas. This competition between two low-emission supply sources is highly inefficient and counterproductive in the longer term. Competing uses to deliver maximum carbon dioxide abatement potential. The world's finite natural gas resources need to deploy to avoid coal emissions where possible. Competing uses, such as extraction of oil from tar sands, have serious negative consequences for the climate and should be avoided. Shrinking sources of supply. Gas resources have been available in many areas and often close to the markets that use them, such as North Sea gas in Europe. However, as these are used up, the focus moves to the remaining large gas reserves in areas remote from current and future high-growth energy demands. The global leader by volume proven is Russia, 47.57 trillion km, followed by Iran 26.62 trillion km, and Qatar 25.77 trillion km. European production is now in severe decline, with increasing dependency upon Russian supplies. This raises challenges for transportation and energy security. Transport and storage. It is more difficult and often more expensive to transport and store gas compared to liquid fuels such as oil or solids such as coal. Traditionally, gas has been transported via pipeline from source to production and then onward to market via other distribution networks. Pipeline investment requires stable long-range contracts, low sovereign risk, harmonization of financial, supply and demand risk, and strong regulatory design with interaction between and across markets. Some networks have existed for over 100 years. In deregulated markets, there is usually third-party ownership of transportation assets outside the controls of producer and end user. This presents further risk. On the other hand, liquefied natural gas (LNG) is usually transported in shipping operated by producers or end users. Russia has an extensive pipeline network linking its reserves to Europe, China, and Japan. By contrast, Qatar has recently commissioned 46 new LNG tankers which can be delivered by South Korean shipbuilders in about 3 years, compared with a 10-year lead time for pipeline developments. Methane leaks. Natural gas consists primarily of methane CH4, which is 21 times more potent than carbon dioxide as a greenhouse gas. As such, relatively small leakage. Carbon capture and storage (CCS). Carbon capture and storage (CCS) is a relatively new way of reducing carbon dioxide emissions into the atmosphere. It refers to various technologies which initially may be applied on a large scale with large carbon dioxide point sources and may in future be applicable on a smaller scale. Carbon capture involves separating between 40% and 95% carbon dioxide during or before mining of any fossil fuel pre-combustion capture. It can also occur during a gasification/decarbonization process of the fuel used. Gasification of coal (IGCC), for instance, results in hydrogen H2 as the combustible product. All other pollutants, including carbon dioxide, are separated and can be removed. Carbon dioxide can also be removed during and after combustion in a fossil fuel-fired power station post-combustion capture. In the future, carbon capture may be also possible for non-energy CO2 emitting sources such as cement and steel production. The storage part of CCS refers to the process of re-injecting the carbon dioxide into deep geological layers, thus isolating it from the atmosphere for a long time. Between capture and storage, liquid carbon dioxide is transported to the geological storage site, e.g., via conventional pipelines or ships. Although CCS is new, its components are not. For instance, pre-combustion capture is widely applied in fertilizer manufacturing and production of H2 as a chemical feedstock. 35. JMG sees CCS as mitigating the negative consequences of the possible renaissance of carbon-intensive king coal in times of more costly and apparently less reliable supply of other fuels. Coal is more carbon-intensive than oil and much more so than gas, so it is less desirable from an emissions point of view. But almost 60% of global natural gas reserves occur in three nations: Iran, Russia, and Qatar. Based on current production rates, economic reserves of gas are expected to last for 65 years. In the similar case of oil, about 3/4 of all reserves occur in 7 nations, including Russia, Venezuela, Saudi Arabia, and other OPEC Gulf nations whose economic reserves are expected to last for another 40 years. In comparison to oil and gas reserves, coal is much more abundantly available, especially in those countries which are large energy consumers such as the United States, China, India, Russia, and Europe. Here, political concerns on security of supply and the high costs of nuclear fuels may continue to drive an interest in coal at least for some time. In the last 4 years, global coal consumption has risen by 22%. 36. Long-term fuel supply scenarios see coal gaining ground to more than double its power production contribution. Hydroelectricity. This brief covers 3 related technologies with a proposed capacity of plus 400 GW. Repowering old hydro dams plus 30 GW proposed, and installing new small plus 100 GW, and medium and large hydro projects plus 270 GW. Hydroelectricity currently provides nearly 20% of the world's electricity. At particular sites, hydroelectricity can provide low greenhouse gas emission electricity that is particularly useful for meeting peak loads. Issues which arise or constraints which should apply to its widespread deployment. Dams destroy the ecology of river systems by changing the volume, quality, and timing of water flows downstream, and by blocking the movement of wildlife, nutrients, and sediments. Less than 40% of the world's longest rivers remain free-flowing, and there are over 1,400 large dams planned or under construction, e.g., 105 in the Yangtze River Basin ecoregion, 162 in northern India. Dams have enormous social impacts, with 40 to 80 million people displaced so far. Large dam proposals at many sites have been opposed by local people, undeveloped but not necessarily a low impact or sustainable. Hydropower capacity is unevenly distributed. 60% in Asia, 17% in Africa, and 13% in South America. Small hydropower is mostly used in decentralized systems. Development deployment potential. Repowering old hydropower dams, retrofitting them with modern equipment that can produce more power generally is benign and can be an opportunity to reduce the original environmental impacts. While the total contribution is relatively small, plus 30 GW, repowering of dams can happen quickly and form the basis for a broader dialogue between civil society and financiers, industry, and governments. The 30 GW contribution is estimated based on the numbers of 20-plus-year-old hydropower-only dams on the International Committee on Large Dams register and estimating a conservative 10% increased production between now till 20 GW and 2025 plus 10 GW based on a mixture of light, medium, and full upgrading opportunities. Small, low-impact, economically feasible hydropower potential is estimated at 190 GW globally, with 47 GW developed so far. We have estimated that a realistic development level is around 100 GW over 50 years, continuing the current 2 GW/year growth rate. New dam proposals are controversial. Based on impacts in countries with different degrees of hydropower development, JMG estimates that it may be possible to develop 30% of the economically feasible hydropower capacity in most river basins or nations without unacceptable impacts, in accordance with World Commission on Dams guidelines. Around 740 GW has been installed out of a global economically feasible large hydropower capacity of 270 GW. Around 120 GW are currently under construction and 445 GW are planned over 30 to 40 years, including many dams with unacceptable environmental impacts. We estimate that of the 445 GW, 250 GW of large hydropower sites could be developed with relatively low impacts. Using a similar process, we identify a further 20 GW of medium